Alright, guys, we have to face the facts. We are simply not made to reach the deepest, darkest points in the sea. Our bodies are ill equipped to deal with the incredible pressures, and even oxygen becomes unsafe if we go deep enough. But what happens if we expose something else to the pressure so we don't feel any change? Today, we try just that, descending into the deep without getting a drop of water on us. Today, on episode 4 of Full Ocean Depth, we discuss submersibles and submarines. This is the penultimate episode of this series. If you're new around here and like what you see, consider subscribing, and make sure to check out the last few episodes. Anyway, let's get into it. Here's a concept I had to learn for this series. Stress. No, not the kind you get when you're doing things that you shouldn't and someone walks into the room.
Gary!
I'm talking about physical stress. The same thing we've been experiencing each time we dive down and expose ourselves to higher pressures. This is something I never learned in physics class, as it's much more relevant to engineers and not so much for a marine biologist. So I had to ask an engineering friend how it works. Brace yourself for this, because I need to introduce a bunch of stuff to you here. I'll do my best to keep it easy to understand, but considering I need to explain a bunch of new physics concepts at once, I make no promises. Here's the equation for stress. We haven't discussed any of these factors yet, so let's briefly introduce them. Sigma represents stress, the thing we're calculating for. F is for force, a key element throughout all of physics and measured in newtons, named after the inventor of gravity himself. A means area, which is just length times width, super basic geometry that if you're smart enough to click on this YouTube video, you probably already understand. Force can sometimes be calculated by multiplying pressure with area, so this equation is really just stress equals pressure multiplied by area, all divided by area. So far, I have expressed pressure as pounds per square inch, but in physics as well as the rest of the sciences, we use the metric system, in which pressure is measured in pascals. 14.7 psi, 1 atmosphere worth of pressure, is 101,352.9 pascals. Okay, I think that should cover everything we need to know. Let's try an equation now. Aluminum alloy 6061-T6 is used to make scuba tanks. Take a block of it and put some pressure here. Let's say it's 500,000 pascals. The area of the surface we're applying pressure to is 2.5 square centimeters, aka 0.00025 square meters. That means the force applied is 125 newtons. Now to calculate stress, we take that force and divide it by the area, and in the end we are left with our pressure from the start, 500,000 pascals as our stress. But what does this even mean? And why did I have to specify the aluminum? Well, every material has a yield strength and an ultimate tensile strength, and our particular aluminum alloy has a yield strength of 241 megapascals, or 241 million pascals, and an ultimate tensile strength of 290 megapascals. Looking back at our 500,000 pascals of stress, it's safe to say our block of aluminum isn't changing shape. Just to clarify, yield strength is the point in which a material begins to deform, and ultimate tensile strength is the point in which a material will break. Here's a couple more materials that will be relevant and their respective stress limits. And because I know some people will ask about this, here's the stress limit of carbon fiber reinforced plastic, the material that's used in the production of modern planes, and that one submersible. We make planes with it because it can flex and bend, so when turbulence hits, a wing doesn't snap off. Its stress limit is way higher than the others. So what gives? The actual stress limit is highly dependent on the orientation of the fibers and how they're held together. Also, repeat exposure to high pressure will lower its stress limit. So when you make a submersible out of materials used to make planes and repeatedly send it to extreme pressures, You shouldn't be surprised when it doesn't end well. Now that we've got all that out of the way, let's talk about the differences between submersibles and submarines. The reason the words submarine and submersible exist are because they are indeed different things. Let's discuss the former. Submarines are naval vessels that cruise around beneath the waves and get from point A to point B on their own power. This is what transported our Ivy Bells divers from the last episode. Submarines are used almost exclusively by militaries around the world for their ability to move throughout the oceans while remaining undetected. At least the good ones are. I'm talking about NATO subs, none of that noisy Soviet-era stuff. The Ohio-class American nuclear ballistic missile submarine is likely the most advanced submarine in the world, with a length of 560 feet, a crew of 15 officers and 140 enlisted men, carries 24 city killers, and is powered by a nuclear reactor that allows it to remain below the waves as long as the crew has enough food and can stay sane enough around each other. Its unclassified diving depth is 800 feet, but it is likely significantly deeper. Submarines ascend and descend thanks to their ballast tanks. These components are filled with either air or water, depending on if the submarine is on the surface or at depth, by affecting its buoyancy. Buoyancy, or an object's ability to float, is determined by the volume of air within the object. Take an aluminum can and put it in the kitchen sink. It floats. Now crush it and put it back in. It sinks. That's because the volume of air inside has decreased, while the amount of metal has remained the same, and so it is no longer buoyant in water. A submarine will flood its ballast tanks to descend, because replacing the air inside with water decreases the volume taken up by air and reduces the submarine's buoyancy. To ascend again, pumps are used to remove water from the ballast tanks, increasing the submarine's buoyancy. Now it's time to talk about submersibles. Submersibles are similar to submarines in that they are intended to allow people to dive deep without getting their feet wet. However, they do not get out into the middle of the ocean on their own. The tiny thrusters you see on submersibles are only good at making small adjustments and couldn't power this thing for too long. No room on board for a nuclear reactor this time. These underwater vessels require the assistance of a surface ship to bring them to their diving point, and so are either reserved for the rich or research organizations and universities. This is Alvin, a submersible built all the way back in 1964 that's still owned by the United States Navy and operated by Woods Hole Oceanographic Institution. She's made many scientific discoveries during her decades of service, and to keep it brief, she has seen some stuff. In 2022, Alvin got her most recent upgrade package and is rated to safely dive to 6,500 meters. She functions similarly to that of our nuclear submarines and other submersibles in that she uses ballast tanks to ascend and descend. Now, there are a couple reasons Alvin can't dive deeper. One is, of course, the previously described stress limit of her hull, and while mathematically she should be able to dive deeper, for obvious safety reasons, that chance is not taken. The second reason is the ballast tanks. Those pumps that push water out have to pump it into the pressurized water outside the submersible. And at 6,500 meters, that water is 651 atmospheres, nearly 10,000 psi. That takes some serious power from the pumps to move water out, and at our goal of full ocean depth, the water pressure would be too much for the pumps to handle. But lucky for us, at this point in the series, we have learned everything we need to know in order to reach Challenger Deep. All the knowledge we've gathered will allow us to conquer the deepest, darkest depths of the ocean. But that will have to wait until next time. Thank you all so much for watching. This was definitely a learning experience for me, just as much as it probably was for you, as I have no formal training in engineering. I want to give a shout out to my good buddy Jared for his help in writing this script. He is an engineer and is much better equipped to talk about this stuff. I really wouldn't know how to go about making this episode without him. Anyway, that's all I got for you today. You all have yourselves a good one, and I hope you learned something.